Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for week number 7 for wireless and mobile communications. In our first lecture, we talked about measurement based model named as Okumura model, and I discussed that Okumura model was based on a measurement scheme conducted by Professor Okumura and their team in Japan back in 1960s, and on the basis of those measurements they generated some curves, and those curves were enabling us to calculate path loss for different types of environment and different distances and different antenna heights. So this was the discussion related to our previous lecture. Let us continue the same discussion. When I was trying to explain the empirical models, in that case I mentioned that there are variety of different empirical models which have been proposed in the literature. So the Okumura model that we discussed in our last class was only an example, and you must expect that there are variety of other models which are based on different measurement campaigns and which are in use for different types of environment. The main drawback on the measurement based models is that they are actually applicable to the type of environment which is similar to where the measurements has been conducted. So in order to make a generalized model, we need to have a detailed measurement campaign where we take measurements in variety of different scenarios, as was discussed in the Okumura models. One of the drawback of Okumura model was that it was based on some standard curves, and we have to rely on those curves to estimate the path loss. An extension to that Okumura model was made by Hata, which is sometimes named as Okumura Hata model. What Hata did, that Hata transformed the information which was incorporated in the form of graphs in Okumura model into empirical relationships. So instead of using those graphs, you can use empirical formula, or those mathematical formula enable us to calculate the path loss for different type of environment. And those models, the Hata model and Okumura model, they closely agree with each other when we have large distance, as I discussed in the case of Okumura as well, that those models are valid for distance greater than 1 kilometer or up to 100 kilometers. So Hata model is actually, you can take Hata model as another form of Okumura model, where the graphical information is actually incorporated in form of mathematical formulation. So it makes a more convenient model when we try to implement that thing in any computer software, or we are trying to analyze any type of system. The limitation of the model is that it's actually based on a distance greater than 1 kilometers. So this model is applicable to a relatively larger distance with a specific frequency band. And for most the personal communication system which we have for the smaller distances of the order of 1 kilometer or less, for those cases we cannot use this Hata or Okumura model. For Hata model, actually the environments were divided into three different categories: urban areas, suburban areas, and open areas. So there are formulation which we can use to calculate the path loss for these three types of environments. So let us move on. So this is the formula for Hata model. This 69.5 is a constant number, 26.16 log fc is the carrier frequency or operating frequency, HTE is effective transmitter height, HRE is effective receiver height, and again we use HTE here. D is the distance between transmitter and receiver, and this A is a function of HRE. So these are the conditions which are given. FC is the frequency which should be taken in megahertz. For this model, the frequency range that we use is from 150 megahertz to 1500 megahertz. So Hata model is applicable for only this frequency band which we use. HT is effective transmitter antenna height, which for cellular communication system, which is actually referring to base station antenna height. We take this antenna height to be in meters, and that height ranges from 30 meter to 200 meters. So this model, the Hata model, is applicable to this antenna height range. HRE is effective receiver or mobile antenna height. Again, this height should be taken in meters, and this HRE for this particular model is taken in between 1 meter to 10 meters. So HRE, the applicable range for HRE is 1 meter to 10 meter. D is the transmitter receiver separation, which is taken in kilometers. You must take care of the units as well, because this model is based on a specific units. Antenna heights are taken in meters, whereas the distance is taken in kilometers. A of HRE. This A is actually is a correction factor. Like if you recall, in Okumura model we use a correction factor and represent that by G. In Hata model, the correction factor is represented by A. So AHRE is actually a correction factor which is based on the effective mobile antenna height, and this correction factor is actually a function of size of the coverage area. So this is the generalized formulation for that model, and you can see that FC, generally as FC is known, HTE, which is transmitter antenna effective antenna height, is also known. D is also known. HRE is also known in certain cases, but we need to calculate AHRE. How can we calculate AHRE? It depends on the coverage area or type of city where your mobile is being used. So if you have a small or medium sized city, the mobile antenna correction factor is given by this formula. AHRE is actually 1.1 log FC, HRE minus 1.5 log FC minus 0.8, and this thing is in actually dB, is decibel, and you must see that this previous relationship is also in decibels. You can see here this relationship which is given by the Hata model is also in decibels. So AHRE is also in decibels, so this is the model where you this is the correction factor which we use when we have a small or a medium size city. But in case of a large size city, in that case this AHRE has two different expression depending on the operating frequency. So if you have operating frequency which is smaller than 300 megahertz, we use this relationship to calculate the correction factor, and if you have operating frequency which is greater than 300 megahertz, in that case we use this relationship in order to calculate the correction factor for effective antenna height. For suburban areas, if we have suburban area, in that case we need to make some correction as well, because as we discussed in the case of Okumura model, that this baseline formula is actually calculated on the basis of urban environments. So this formula is applicable to urban environment only. Whenever we have suburban environment, in that case we need to provide some correction in that formula, and that correction in Hata model is given as this part. So this L50 urban is the same formula that we use, which I showed previously. and this is the correction factor, which is actually dependent on the operating frequency. Similarly, if you have an open or rural environment, open areas, in that case, again we would be needing some correction factor in that the urban area path loss formula, this formula. So this first part is actually the urban area path loss, which will be calculated by standard Hata model, and the rest of the part is actually the correction factor, which is applied whenever we are working on the open rural areas. So for open rural areas, you can see that this correction is also is again dependent on the operating frequency. Okay, as I mentioned that this model, it's actually applicable to larger distances, and generally the smaller communication ranges, they are not covered in that model. Later on, a European Society Cooperative of Scientific and Technical Research, Eurocost, actually this cost, they had certain models. They also proposed certain model for different environment. They constituted a committee to extend the Hata model. So this is generally known as COST 231 model. COST 231 model is actually an urban environment which actually extends the Hata model for up to 2 gigahertz. So this revised formula, which was proposed by COST 231, is actually based on the Hata model, but this is applicable to relatively larger distances, because the previous formula that I showed, this was applicable to 1500 megahertz only. So if you have frequency from 1500 megahertz up to 2 gigahertz, so operating frequency is between 1500 to 2 gigahertz or 2000 megahertz. In that case, we can use this formula. L50 urban is given by this formula, and we have additional correction factor, which is written as CM here. This CM is actually dependent on the type of environment. If you are using a medium sized city or a suburban area, in that case this CM would be 0. But if we have metropolitan city or a larger city, in that case this CM comes out to be 3 dB. So you would be adding a 3 dB here. So this model extends the applicability of Hata model up to 2 gigahertz range, and rest of the stuff is same as we discussed for Hata model. So this was our discussion related to outdoor propagation models, and we discussed actually two models. First one is Okumura and second is Hata model. Okumura was basically relying on the curves which were generated, and Hata model is actually based on the mathematical expressions to calculate the path loss. I must reiterate that these are not the only models. There are certain other models which we are not going to discuss in this course, but for different types of environments there are different models which have already been proposed in different literature. So these models, Okumura and Hata model that we have discussed here, they are discussed to provide you an overview how these models are generated and how to use these type of models. So now let us start our discussion on indoor propagation model. The previous Okumura and Hata model, they were primarily outdoor propagation model, but when we are starting the specialized communication systems which are using indoor propagation, and like the personal communication systems, we generally need to characterize the radio propagation inside buildings. So for inside buildings or indoor propagation, the nature of channel is relatively different than the traditional outdoor mobile channel. The primary difference between the outdoor and indoor channel is that the first thing is that the distances which we have to cover in indoor, they are significantly smaller as compared to the outdoor propagation. So generally when we are talking about outdoor propagation, we talk in the distance ranges having the range of kilometers. 1 kilometer, like Hata model, was applicable to 1 kilometer to 100 kilometer. But when we are talking for indoor propagation, we generally have distances which are of the order of meters or tens of meters maybe. So this indoor propagation is based on relatively smaller distances. Second important thing is that the indoor environment, they can have variety of different variations. Even for the small TR separation, the environment is can be very much different. For example, if you are talking about propagation between two rooms, so whether the door between two rooms is open or not, it significantly changes the behavior of the propagation. For open doors, you may have a line of sight communication with significantly smaller loss, and when the door gets closed, in that case you may get significantly larger loss. And the propagation within the building, they depend on variety of different factors. For example, how the building is constructed, the layout of the building, the construction material, because different materials, they exhibit different losses, the type of the building that you are using, whether it's an office, a small residential area, or a large factory, or what type of building you are using, it also affects the propagation. So the summary is, the indoor propagation model is not easy to generalize, because there are a variety of different combinations which are possible in indoor environment. So generally we rely on the measurement based campaigns in order to model the indoor environment. And in different literatures, different researchers has already worked on different types of measurement campaigns in order to propose a suitable model for indoor propagation. For this course, let me discuss few of them, and I'll try to provide an insight how different aspects are covered in these measurement campaigns. So first important thing is that the indoor propagation is actually also dependent on the same phenomena as we discussed for outdoor propagation. So primarily the electromagnetic phenomena that govern the indoor propagation are reflection, diffraction and scattering. So all these phenomena are also available in indoor, but the problem is indoor environment is more cluttered, and there are variety of different stuff, and the deployment can be in different scenarios. So signal depends on the layout of the buildings and interiors. Moreover, the indoor propagation also depends on the antennas, how the antennas are mounted in an indoor environment. They also affect the overall propagation. So you can take an example that if we compare an antenna which is mounted at a desk with an antenna which is mounted on a ceiling, so you would see that in both cases the signal strength at the receiver side at a equal distance would be different. So the propagation for both types of antenna would have different effects. In most cases, we try to classify indoor environment as having the line of sight or obstructed environment. So generally there are two cases whether we have line of sight available in indoor, or whether we do not have line of sight available, or it's obstructed by any obstruction. The obstructions which are present in indoor environment, they can be a variety of different nature. For example, in common household building, we generally have hard partitions. Hard partition like the walls or maybe wooden separation that starts from floor up to ceiling. So these hard partitions, they are part of the building structure, so they span to the roof level. There are sometimes soft partition. For example, if in an office environment, sometimes we use soft partition where we make maybe human height partitions to separate different cubicles for different types of works. So they are movable partitions, and they generally do not span up to ceiling. The problem is this partition can be made of different structures. For example, if in certain environment the partitions are made of aluminium, and in another environment the partitions are made of wood, or in some cases the partition may be made of glass. So all these three partitions, they would behave differently for indoor propagation. So that material which is used to make the partition is also cause significant variations in that propagation. So different researchers has studied different types of partition and different types of environment, and our textbook has summarized results from different researchers and presented those results in form of table 3.3. So that table is actually a good collection for losses that we can expect from different types of materials in an indoor propagation. Let me show you a small portion of table 3.3. This one is not the complete table 3.3. If you go to book, you would see that it's a long table where different types of materials and their corresponding losses they have been discussed. But in order to give an overview, I just picked a small portion of that table. So for example, Cox in his work, he studied a effect at the frequency range of 815 megahertz, and he saw that if the communication is blocked by an all metal blockage, in that case you would expect a loss of 26 dBs when the signal passes through those metal based obstructions. Similarly, Cox in his paper for 815 megahertz frequency also discussed the aluminium sliding cases, because sometimes we made doors made of aluminium sliding. So whenever there is a aluminium sliding partitions, in that case the loss is around 20.4 dB. If there is a foil insulation, again at the same frequency 815 megahertz, for foil insulation you would you get a loss of 3.9 dB. Rappaport in his paper in 1991, he studied the behavior of at 1300 megahertz. So these are the results which are presented for 1300 megahertz for different types of partitions. So if we have a concrete block wall, which is common in our society, so when signal propagates through a concrete block wall, so you get a loss of around 13 dB. So whenever signal propagates from one floor to another floor through a concrete roof, in that case you get a loss of around 20 to 30 dBs. Similarly, if a signal propagates from one floor to another floor and also crosses a wall, so it's two different obstructions, one wall and one floor, in that case the loss is around 40 to 50 dB, and so on. So this entire table 3.3 is worth looking at. You would see that variety of different materials have been studied in literature, and the corresponding losses at the operating frequencies are also recorded. Again, I must say that these tables, this would give you a understanding, but sometimes if there is any other situation, so you may need to have a measurement campaign, or maybe there may be a different model for that as well. Okay, so first thing that we discussed about in indoor propagation was the partition loss. Whenever you have a partition or obstruction between transmitter and receiver, in that case we encounter a loss, which can be calculated by measurements as well as some standard results which have already been reported in literature. Sometimes we use propagation where the signal propagates from one floor to another floor. So say for example, if a signal goes from one floor to other, in that case there will be loss. For example, if you look at this Rappaport's paper, the loss from one floor for other floor is actually around 20 to 30 dB. But this loss is actually dependent on variety of different stuff. The Rappaport's work was only based on the concrete material, but generally it also depends on the dimensions. If you change the dimension, the loss gets changed. The material, the construction material that has been used for that particular building, it also affects the loss. The type of construction to create the floors is also affects the losses that we exhibit between floors. The surrounding stuff also affects the losses. Number of windows which are present in those buildings, they also affect the losses. So basically there are variety of different parameters which actually affect the losses when the signal propagates from one floor to other floor. Different researchers has done the measurements in order to calculate the loss or attenuation between floors. In textbook you can see that there are two tables, table 3.4 and 3.5, which provide some results which are related to calculation of losses when the signal propagates between two different floors. For this discussion, I am sharing a table 3.5. You can see that the table is based on the measurements made in office environment. So there are two different types of office building 1 and office building 2, and for that the loss was calculated. So two things were calculated. First was floor attenuation factor. This FAF is actually representing the floor attenuation factor. So how much attenuation would you expect when the signal propagates through the floor? And this is actually sigma is representing the standard deviation that was measured when they took measurements at different locations. Also the table also provides the number of locations where the measurements were taken. So for these cases the measurement was taken for 52 locations and 9 locations, and for this, for office building 2, measurements were taken at 21 different locations, and on the basis of those measurements these results were calculated. So you can see that if the signal propagates through one floor, in that case you get a attenuation of 12.9 dB. If it goes through two different floors, the attenuation is 18.7 dB. For 3 floors the attenuation is 24.4 dB, and for 4 floors attenuation is 27 dB. You can see that there is an interesting thing that when number of floors get increased, the relative attenuation is not increasing at the same rate. For example, if for the first case you had an attenuation of 12.9 dB, for 2 floors for second floor the additional loss was only around 6 dB. For third floor the additional loss was around like 5.5 dBs. For fourth floor, the additional loss was around maybe 3 dBs. So when the number of floors gets increased, the attenuation does not increase at the same rate, and the standard deviation is also decreasing. You can see that for first case the standard deviation was high, but at higher floors the standard deviation was relatively low. But in the second case, you can see that the first type, for first floor you have attenuation of 16.2 dB. For two floors the attenuation was 27.5 dBs. The addition was around 11 dB, and for third floor that addition was only for maybe 4 or 4.5 dBs. So you have attenuation of additional attenuation of only total floor attenuation factor of 31.6 dBs. So this is how you actually represent the floor attenuation factors in order to see how much attenuation you would get when the signal propagates through floor. So these tables that I have discussed so far, they are generally based on the measurements, and on the basis of measurements the models the attenuation was calculated. One of the common model that we use for indoor propagation as well as the outdoor propagation is the log distance path loss model that we have discussed previously as well. In indoor propagation we can also use this log distance model because it's a generalized model where you have a specific value of n, and that n actually dictates how much loss would be there. So the path loss that you encounter with log distance model is dependent on the distance raised to power certain path loss index n, where n is sometimes calculated on the basis of measurement. We did a problem previously for outdoor measurements and calculated n in that problem. Similar type of measurements and calculation can be made to calculate the path loss index for indoor environments as well. So this is the loss in decibels. The same expression is represented in decibels. So if you know the loss at a reference distance d naught, and you know the path loss index, so you can calculate the total path loss in decibels. And also, as I mentioned previously, that there is some randomness available in those path loss measurements. So path loss actually represents the median value of the loss. So in order to represent those randomnesses, so we generally add a shadowing random variable x sigma, where this x sigma is actually normal random variable, of course in decibels, because the entire expression is in decibels, which has a standard deviation of sigma dB, and the mean value of this x random variable is taken as 0. So this log distance path loss model can also be used for modeling the indoor propagation, and we can calculate this path loss index n by taking measurements in the particular indoor environment where we want to model the propagation. So these are some results reported by different researchers in different types of buildings. They actually took a variety of measurements in different types of buildings and calculated path loss index as well as the standard deviation on those measurements. So for example, for retail store at a frequency of 914 megahertz, the path loss index is around 2.2 with the standard deviation of 8.7. For a grocery store, the value of n is found to be 1.8 with the standard deviation of 15.2. When we have a hard partitioned office environment, in that case we have 3 path loss index with 3 path loss index of 3 with the standard deviation of 7. But with soft partition, the path loss is relatively lower. As you can see that the path loss index is smaller, which is 2.4 at 900 megahertz and 2.6 at 1900 megahertz. So different types of factories where LOS environment is available. These results report the losses, the path loss index in that type of factories, different operating frequencies. Similarly, for suburban homes at indoor streets, you can see that path loss index is around 3, and the standard deviation is 7. The obstructed factories, they also have certain loss, which is as expected is greater than what you expect from the LOS building. So in that case, this loss is 2.1 and 3.3 when you have obstructed environment. Another important model is sometimes known as attenuation factor model, where we model the environment as a single storied environment, where with some floor attenuation factor in order to incorporate the effect of more floors. So this NSF, actually this part is same as the log distance model as we discussed previously. NFS is the path loss index for the same floor. So you measure the path loss index for one floor, and on the basis of that floor you can calculate the loss on the same floor. And if you need to calculate the path loss when you are at different floor, so you can simply add the floor attenuation factor, which we have discussed previously. So floor attenuation factor in order to represent the loss between different floors. Sometimes we incorporate these two things, that floor attenuation factor and this path loss index for same floor, in a new path loss index, which is the path loss index for multiple floor separation. So NMF is actually path loss exponent based on measurement taken at different floors. So sometimes you can use the same log distance model to represent the path loss where you have multiple floors. So this table is actually representing the path loss exponent for different types of buildings with different floors. This is actually for multiple floors as well, where some of the measurements are represented for same floor and some of the measurements are represented for multiple floors. So you can see that you can calculate the path loss on the basis of measurements taken at maybe same floor or different types of floor, and you can calculate the path loss index and the standard deviations. Okay, so these are some of the discussions, discussion related to some of the models which are actually representing the propagation in an indoor environment. So we conclude our discussion on indoor propagation here. We have discussed a variety of different models, and in the last we also discussed this log distance path loss model. So this is one of the most commonly used model to represent the propagation in indoor environment as well, and the same model can also be discussed, can also be used to model the propagation in an outdoor environment. So this concludes our discussion on the large scale modeling. We discussed variety of different environment and different models, starting from free space model, then two-ray ground deflection model, to log distance model, and then we discussed outdoor propagation and indoor propagation. So I hope you have a good idea how we model the channel behavior on the large scale by using these path loss models. So we conclude our discussion, as well as the chapter for the relevant chapter of the book is also completed here. So we will start a new topic in the next lecture, inshallah. Thank you all.